Okay, so we just kind of did a recap, and so we looked at, put up some, put the reminders all over here. All right, we'll do that. We know that this is an indefinite integral. We know that integrals mean antiderivatives, right? We've gotten that piece. And then we also have, so that was sort of one piece from section 5.1. We've worked on how to do antiderivatives. So we can do basics, which are powers, exponentials, logs, and then we can do reverse chain rules, which you can think of as U substitution, whichever you prefer. So we've got that going on. And then in section 5.4, we learned, well, I guess it's still so multiplication by a constant. And addition and subtraction carry through, just like they have for derivatives. And then lastly, we learned this piece, that if we go from A to C, we can break that up partway through. So this is just kind of everything we know so far. Okay, so now we're going to add what's called, drum roll please, the fundamental theorem of calculus. So it sounds very fancy, but really it's what ties everything together. I'm not going to prove it. We're just going to kind of launch in. Okay, so here it is. Integral from A to B of f of x dx. Remember what we were doing when we set this up. We set this up as being, here's A, here's B, and we divided this up into lots of tiny rectangles, right? And the rectangle went up to the height of the curve. So this is the height times the width. So we're adding up all these tiny rectangles. We're letting the tiny rectangles get really, really skinny. Right? Everyone remember that's kind of the impetus for this. But we also know that this means do the antiderivative. Right? We know that piece. So we know that the integral sign, so we know on the one hand it means add up area, add up rectangles. And on the other side it means do the antiderivative. So now we're going to put them together. This is equal to the antiderivative. Right? Capital F means the antiderivative. Evaluated at, we've used that symbol, that line before, we mean evaluated at, we had a number down at the bottom. Now we're going to have two numbers. These are our limits of integration. So we'll have from A to B. We know when we just had one number, you just plug it in. So what do you do when you have two numbers? How does it mean to evaluate at two numbers? And what this means is evaluate at the top number and then subtract off the antiderivative evaluated at the bottom. Right? So this is actually a fairly straightforward process. To go from here to here, we do the antiderivative. We've done that a couple of days now. Here, we're just evaluating. We've done evaluations for a long time. And so it's a fairly straightforward process. The only thing that I'd like to add is when we do this, notice the difference. Indefinite integral, because there are no limits. Definite integral, definitely from A to B. When I do this one, what is my answer? The antiderivative
Plus C.
plus C, thank you. There's no plus C up here. Why not? Well, let's think about that. If I had a plus C up there, if I said f of x, capital F of x plus C, evaluated from A to B, how would I write that out? I'd say f of B plus C minus f of A plus C. What happens to the plus C's? The plus C minus, they drop out. So because they drop out, are they always going to drop out? They're always going to drop out, no matter what they are. So we don't use the plus C part. So we have indefinite intervals that have a plus c always until you have extra information that you can use to find c, or we have a definite interval where we just don't worry about the plus c. So those are kind of our two categories. Okay, so let's do some examples. Let me write that over there. I'm going to leave it that way, even though it's really f of, well, you want to write that intermediate step when you're actually computing the problem. Okay, so let's look at some examples. So we need to compute that, determine that. If we think about it, the example that we did from 5.4, we already have done this. We could have done that because we happen to know, let me write over here, we need this, from 2 to 3 of x squared was 19/3. That was from before. Times 6 would be just 6 times that, so 6 times 19/3 is canceled to 38. So I expect an answer of 38. Based on what was presented earlier. So this actually didn't come from nowhere. That's actually the correct answer. So let's look at how we get from here to there without using this information given. So anytime I have an integral, what do I know I need to do? Integral says the integral sign says do the antiderivative. So what's the antiderivative of 6x squared? Is this a basic?
Yeah.
Yeah, it's just x squared, right? It's a power, so that's a basic, so that's good. So this is a basic, it's a power, so that means I raise the exponent and divide by. You could go straight to 2. I mean, 6 divided by 3 is 2, so you could do that. Evaluate it from 2 to 3. So let's just clean that up. 2x cubed evaluated from 2 to 3. All right, so now we just start plugging in. Plug in the top number first. And now you have a choice. You can pull this 2 out front and evaluate, or you can have the 2 tag along. That's kind of a your choice sort of thing. I'll have it tag along.
Can you plug from the bottom up?
No, top minus bottom.
But you always see it from the bottom going somewhere.
Yes, so if I wanted to add up, let me give you an example. So I've got a set of numbers. I have the first number. This is going to be that. I go from 0, 5, 10, 12. If I wanted to add up from 5 to 12, how would I figure out what that distance is? I would say 12 minus 5. The top number minus the bottom number. So even though we add from 5, you want to know how many numbers going from 5 to 12? When we actually figure out that distance, that difference, it's going to be 12 minus 5. So yes, we are starting at 2 and going to 3, but it's kind of like saying 3 is my top point, so to find how far I went, I have to subtract. All right, so 3 cubed, 3 cubed minus 2 times 2 cubed. 3 cubed, 27, 54, 16. What are we going to get? Exactly what we should have gotten. So this is the whole problem. This is it. Now clearly this can be a little more complicated than that, right? This piece can be more complicated, but this is and you can have fractions, right? But this is how it works. So you're presented with this. You say that means this says do the antiderivative. This says evaluate it from 2 to 3. So we put in 3 and then subtract and put in 2. I strongly recommend, we're going to get to some, using parentheses when you're going to subtract more than one thing, just to make sure that your negative sign carries through properly. Okay, so let's do another one. Let's do right, let's do this one. So, is it a basic? Is it of the form x to the n, e to the x, or 1 over x? It's sort of getting to this, but is it any one of these exactly? No, so it's not a basic. So what is it? Of these three, what does this look most like? Looks like a ln because, and here's, remember, whenever you have a denominator like this, you need to check. It could be a ln or it could be a power. The way you know is you take the entire derivative of the bottom. So the derivative of the bottom is 2. Is that in the top? Yeah, it is, except we don't really care about numbers, right? We can smush around numbers. If I had any variables, they would have to be in the top. So the entire derivative, I can say that this is, I can multiply by 2 in the top. If I multiply by 2 in the top, what else do I have to do?
1/2.
1/2. Or we'll do this way, and then we'll do it again, use substitution. Okay? Because I know for ones like this, sometimes use substitution may be a little bit clearer for this one. Okay, so now what do I have? Is the derivative of the bottom in the top? Yes, that means it is ln of the bottom. So 1/2 carries through on the outside. Ln of 2x plus 4. And then I'm going to evaluate that from 0 to 1. Anytime you're going to get ln of anything, ln of 1 is 0. Aside from that, you're going to get, just go ahead and use decimal, that's fine. Or leave it exact. So here we'll have 1/2 ln, put in the 1, so 2 plus, so ln 6, minus 1/2. Put in 0 would be ln 4. Just for kicks, just because I know you guys love this stuff so much. Let's combine those. Let's combine some, do some logs. What do I know? So I can factor out a 1/2. I'll have ln 6 minus ln 4. Ln 6 minus ln 4. What do I know? If I subtract on the outside, what happens on the inside?
Division.
Division, yes. So this would be 1/2 ln 6/4, or 1/2 ln 3/2. What does the 1/2 on the outside do? What can I do with that?
Comes the exponent?
Yeah, exactly. This, remember, can come up here. It can go in either place. So then I can have ln 3/2 to the 1/2. That's an exact answer. You can also plug it in a calculator at any step. You could have plugged it in the calculator here. Any of these steps is fine. This is the exact answer. Whatever you get from the calculator will be approximate. So is this a basic? No, because it's not, strictly speaking, this. When you have a denominator, you need to check ln and power. If the derivative of the entire denominator is in the numerator, then it's a ln. Otherwise, you need to rewrite for power. So let's look at the next one, because that will be a good example of that. Oh, wait, shoot, I was going to do this one. Let's do this one, use substitution. Let's do that again. All right, so what do we have? We had 0, 2, 1. Okay, so let's say I wanted to do this use substitution instead. The whole point of use substitution is to substitute u to make something a basic. So if I could make that whole denominator u, then I would have 1 over u, right? That's a basic, that's a ln. So I'm going to say let u equal 2x plus 4. That's going to simplify that denominator into a basic. That means, though, that I have to get rid of everything that had an x in it. So that means I need to get rid of the dx. So du will be the derivative of this, 2 dx. Okay, so now I have, but do I have a 2 dx? I don't. So you have a couple of options here. You can put in the 2 and the 1/2. Or you can say, well, I have the dx. So I could just solve for dx alone by dividing both sides by 2, and that'd be a half du. So everywhere I have a dx, I put in a half du. That works too, so either way. So then this will end up with, I'm going to leave off my limits for now. We'll talk about that in a sec. So I'll have 1 over u du 1/2 out front. Is that a basic? 1 over u, that's a basic, that's just the ln, right? So that means that this, everyone see how I got from here? So I plugged it, this got replaced with u, this dx became a 1/2 du, or if you had wanted to, you could put in the 2 and the 1/2, and then this is the whole du, and there's that 1/2 still. So either you can do it either way to get that 1/2 in the right place. So here we'll get 1/2 ln u. It's not a plus c. I left these off for now because do these limits fit over here? Do x limits work for u? They're different variables. So I cannot put x limits here. I need to have u limits here. So I have two choices. One choice is to go ahead and put the u limits in. If x is 1, if x is 0, u is 4. So if x equals 0, u equals 4. If x equals 1, u equals 6. Those are u limits. That's fine. U limits go with u variables. This is a completely reasonable way to do it. And so then I would get 1/2 ln 6 minus 1/2 ln 4, which you should recognize is what we got before. So that this is an important thing. This is actually kind of jumped ahead in my notes, but this is an important piece. When you're doing definite integrals, if you want to use u substitution, totally fine. Absolutely. Just remember that you have to either convert your limits so that the whole problem is in u, or you get to this point where you had 1/2 ln u, and you go back to x's. So if I wanted to go back to x's, I would just stick the 2x plus 4 back in. And now I can use my old x limits. So if you're using u substitution, which is totally fine, either go all in, all the way to u, including the limits, or find your antiderivative, back out to x's, and finish in x. So that's the only piece, is that the limits of integration must match the variable. So either way is fine. So how many people prefer u substitution? Anybody in that camp? And how many people prefer the other way? Okay, I was just curious. Either way, totally fine. Okay, so let's do one more, and then we'll do a word problem. Actually, we'll do 2 word problems. Okay. All right, so let's do this one. From 2 to 5 of square root of 6 minus t in the denominator. So, is it a basic? No way. Is it an e? Obviously not, so I'm left with power in ln. Which one is this?
I would do
Power. We're thinking power. Why are we thinking power? Because what is the derivative of the entire denominator? Well, the derivative of the entire denominator would be 1/2 6 minus t to the minus 1/2 times minus 1. Is all of that in the numerator? No. All of that is not in the numerator, so this is not a ln. In order for it to be a ln, the derivative of the entire denominator, all of it, must be in the numerator. That is not the case. So that says then that this needs to be rewritten in power form. So that's a square root, so that's a 1/2. It's in the denominator, so that makes it a negative 1/2. So we'll have 6 minus t to the negative 1/2. Yes?
I mean, anytime you have a denominator that is all one exponent or all one form of a square, I mean, couldn't it just be written as a power rule
Yes.
anyways?
Yes. There are some cases where it's a little bit difficult to tell. I'll do one of those next.
Okay.
There's a,
Because I just thought, like, I don't know, I mean, like, you've been, like, going over, like, working
Yeah.
out the math to see if it's a ln, and everyone that I've seen has just been
Yes, there are, and part of
Either
the
the whole
reason,
thing's an exponent.
yeah,
or-
part of the reason I say
Right.
it is to remind you that the derivative of the entire denominator is complicated. So yes, you should get to the point where you can look at this and go, no way is that a ln, because it's got
It's all
power.
in the negative.
It's, well, it's not just that, it's, let me think of an example where it's a little bit harder to
Right,
tell,
sorry.
but yeah. Okay, so here, now, this is a power. Is it a basic? Is it just t to the something? No, it's a composite. I have one function inside the other. So here's my inside function. The derivative is -1. Do I have that? Well, yeah, it's a number. I can make that happen. So I'm going to put in negative on the outside to compensate for the negative I'm going to put on the inside. Because this piece right here is the derivative of the inside, so I have to have that piece. Or you can get to the point where you can say, if I don't have it, I just divide by. And you don't have to do the rewrite step, that's up to you. Another thing that might be something worth doing is once you know that you have the entire derivative of the inside where you need it, maybe cross it out somehow so that you know you've already, this part gets sucked in back into the inside, you don't have to deal with it. Once you have the entirety of the inside derivative here, you can ignore it. So sometimes it's easy to think you have to still deal with it, but you don't. So now all I have to deal with is the outside function. So that's a power. Multiplication carries through. 6 minus t, -1/2 plus 1 is 1/2. Divide by half or multiply by the reciprocal, that would be easiest. So I'm going to multiply by the reciprocal, so that's 2. 2 to 5. One thing you might consider doing, just because it tends to work in our brains a little bit better, is if you want to, you can just rewrite that as a square root. Again, we tend to think, we always have to write it in power form for doing derivatives and integrals. But we tend to think better in square roots and things in the denominator rather than negative exponents. So I'm going to rewrite this way. That just seems a little bit easier, because I can do square roots better in my head. So -2 times, and here I'm going to pull it out. I'm going to do the -2, this is just another way to do it. I can pull that -2 out front, remember, because multiplication carries through, and now I'm just going to do this part. So the square root of 6 minus 5 is the square root of 1, minus the square root of 6 minus 2, that'd be square root of 4. Or you could have carried the 2 along with each piece. Either, I'm just trying to show you different ways to do it, so either one's fine. So -2 times 1 minus 3, -3. Oh, no, yes, no. 1 minus square root of 4 is 2. So 1 minus 2, -1. So 2. So right now, all we're doing is combining what we know. Integral sign means do the antiderivative. We have basics, and we have reverse chain rules. And then once you've got that, you plug in your limits, do your subtraction, take care with your parentheses, your fractions, all of that. There are computational errors that can be made in this step. On a test, I'm not really worried about that. That's worth maybe like 0.5 point on the problem. I'm just not worried about that. On the homework, it might be a little bit frustrating when you've done everything right up to here and then you misadd in the last step. So just try and take some care. It'll help with frustration. And then lastly, just remember that your units have to match the variables. So if you want to use U substitution, you either need to convert your limits to U or do the antiderivative in U, back out to X and use the original limits. Okay, let's do a word problem or two. I'm going to do on page 373, number 70. I'm going to do number 72. On page 373. All right, so number 72 says the following. For those of you who don't have a book. Maintenance costs for an apartment house generally increase as the building gets older. That makes sense. From past records, the rate of increase, So if they measured year over year, how much more is it increasing? Does that make sense what they're measuring? Where am I? From past records, the rate of increase for a particular complex is given by this. Here's your maintenance increase. Because it's an increase, we know we're measuring it, we've recorded effectively derivative values. How much is changing year over year? 90 x squared plus 5,000. So it's important, these units then are going to be dollars per year, right? Just to help you remember what you're doing. Where X is the age of the apartment complex in years, and M is the total accumulated cost of maintenance. Okay, so write a definite integral that will give the total maintenance cost from the end of the second year to the end of the seventh year. All right, so I want to know total M from year 2 to year 7. From the end of year 2 to the end of year 7, kind of those breakpoints. So do I have M? No, I have M prime. So how do I go from M prime to M? What do I do? Antiderivative. So we're going to set up the integral. Antiderivative of 90x squared plus 5,000. That would be the general answer. I'm looking for I'm just interested in a number, right? Nothing asked me to actually find the functions. I just said, what's the accumulation from year 2 to year 7? So if I knew the total at set, so you could find the function, find plus c if you had enough information, and then figure out what it is in year 7, and then subtract from that what it is in year 2. But you don't have to go through that extra step in the middle of actually finding the whole function and evaluating for c. We can just plug it in here. So does everyone understand how the problem gets from there to here? We're starting with the derivative. We want to know the total over a given interval. So here is the integral, gives me the total, and there's the interval. All right, so let's go ahead and finish this one. So why don't you guys finish this one? You guys work on that, and then we'll kind of compare answers. I'm just writing it out because I think I'm going to run out of video here in just a sec. I got 1 minute. Okay, so did everybody get this antiderivative? Did I do that right? And then it's just a matter of plugging in 7, plugging in 2, and finding the difference. Anybody get an answer for that yet?
I got 35,050.
35,050.
50. It's 35,000.
Like that?
Yep.
Or by the magic of the instructor's edition, but the answer's in the back. It's not written right underneath the problem, like usual. All right, what would be the units on this?
Dollars.
Dollars. Yeah. Yeah. So that's how much accumulated maintenance there is, how much total there was between the end of year 2 and the end of year 7.
I'm just trying to imagine a maintenance company that keeps records